there's one area in the gas law chapter, chapter 10 that we're working in now, that tends to bother students the most. It's probably the gas mixture partial pressure type problems. These seem to be a little bit bothersome, and so I wanted to do one of these as a worked out example. The one I'm going to use is problem 10.64 out of the textbook here. This one basically asks us to calculate, the partial pressure of oxygen and helium in a mixture of the two gases that like a diver might use, and then ultimately what is the total pressure in the tank containing this mixture of two gases. And so, as always, let's take a look at the problem and then let's analyze it and get this thing solved. Now, when we're doing a partial pressure calculation, I'm going to write down over here a couple of things that it's always a good idea to keep in mind when you're confronted with a problem that says, what is the partial pressure? A mixture of gases. You always want to keep in mind a couple of things. For example, the total pressure of a mixture of gases is simply the partial pressure, the pressure of each component in this gas mixture. For us, in this particular problem, it's the pressure of the oxygen plus the pressure of the helium. And in fact, our strategy is going to be, we're going to calculate this one, then we're going to calculate helium, partial pressure of helium, and simply add them together. That's what is going to get us our final result. Now, this is a nice basic relationship for remembering partial pressures, and then I'm going to write this one down. We're actually not going to make use of this version, but when you're dealing with gas mixtures, it's always a good idea to keep this one in mind, that the partial pressure of the oxygen, there are like two different ways to get it. And depending upon the problem and the information provided by the problem, you'll use one or the other technique. One technique for calculating partial pressures is what's called the mole fraction times total pressure. Okay, and so if you knew the mole fraction, and remember what that is the number of moles of O2 divided by moles total. That's mole fraction. If the problem gave you a mixture of gases has a total pressure of 50 atmospheres, what is the partial pressure of the components? This is likely how you would go about solving it. They would have to give you information about moles or stuff to use the ideal gas law to calculate moles, and the total pressure to get the partial pressures. But notice this problem doesn't do that. They come right out and say, calculate the total pressure. And so what we're going to do is instead remember that the partial pressure of oxygen is also directly from the ideal gas law, from our dear friend Piv Nert. I'm going to take Piv Nert, solve it for P. I need the number of moles of oxygen. I need the gas constant, and remember that's constant for any gas, so that doesn't have to be any specific value, one for oxygen, one for helium, or anything else. It's the same value for everybody. And then the temperature of our oxygen and the volume of our oxygen. The beauty of it is we're also going to need to calculate the partial pressure of the helium, and we need, in other words, the moles of the helium, our friend the gas constant, the temperature of the helium, and the volume of the helium. But this is a gas mixture. Once we have the temperature of the mixture worked out, the temperature of oxygen, temperature of helium are the same. Volume of oxygen, volume of helium, since they're in the same container, are the same. The really only difference between the two is the number of moles of oxygen, number of moles of helium. And sure enough, if you look at the text of the problem, they hand us the grams of helium and the number of grams of oxygen. So yes, indeed, this time we're going to get our moles from the good old-fashioned way, the way we know and love. We're going to use grams and the atomic or molecular weights right off the periodic table. Get ourselves moles, plug those in, and ultimately answer the question. So away we go. We are told that we have, there it is, 51.2 grams of oxygen in this tank. All right, if we have 51.2 grams and we know what the gas is, this isn't one of those questions that's asking us to figure out the molecular weight of the gas because it's an unknown. We know what it is, so we know its molecular weight. It's 32 grams of oxygen per mole. A common error I see fairly often from students, you're told it's, grams of oxygen, you immediately think, aha, 16 grams per mole, because that's what you see on the periodic table. But remember, and it comes right out and specifies in this problem, oxygen in the atmosphere is not oxygen atom, it is oxygen molecule, O2. So get the molecular weight written out properly. Doing the calculator dance with that one for a moment, I have 1.6 moles of oxygen. Okay, pretty straightforward there. Now, I am told, and I'm going to write that down here for a moment, that the temperature of this container is 19 degrees C. Of course, we need that in Kelvin, 0.15, and that's going to give me 292.15 Kelvin. The volume of this container, believe it or not, they actually gave it to us in liters. Didn't even have to do any converting. Kind of generous of them to do that. So there it is. I have my moles, I have my temperature, I have my volume. As always in this game, when you're using the ideal gas law, there are 3 of the numbers we need. Calculate the 4th one. Off we go. Pressure, partial pressure of the oxygen here is going to therefore be moles of oxygen, 1.6 moles, times our dear friend the gas constant, 0.0821 liters, atmospheres per mole Kelvin. So many units. 292.15 Kelvin, all over 10 liters. Punch that out on our calculators, making sure our units work out properly. My moles cancel, kelvins cancel, liters cancel. The only unit left this time is atmospheres. I'm calculating a pressure. Kind of convenient it worked out that way. It's 3.84 atmospheres of oxygen. Okay, there it is, partial pressure of oxygen. Now, you repeat that calculation with the helium. We have 32.6 grams of helium. Turning that one into moles, we don't get to do that one very often, but it's kind of fun. 4 grams of helium is 1 mole of helium using its atomic weight from the periodic table. And I have 8.15 moles of helium. Notice, got a lot more oxygen mass-wise, but a lot more moles of helium. Okay, just because of such a light little atom. The pressure of the helium, partial pressure of the helium here, it's almost identical to this calculation. We simply change the 8.15 moles of helium here. The gas constant, I haven't read that they've changed it since we did the first one, so I'll use it again. 292.15 Kelvin, because it's the gas mixture, it all has the same temperature, so I can use this temperature again. 10 liters, and doing the magic calculator dance on this one, I get 19.6 atmospheres. Okay, so the pressure, the partial pressure of the helium is a lot higher than the partial pressure of the oxygen. And then simply the total pressure, the last thing this particular problem wants, is really quite simple now. Partial pressure of the helium, or a partial pressure of the oxygen, atmospheres O2, plus partial pressure of the helium, 19.6 atmospheres helium. And we punch that out on our calculators, 23.4 atmospheres total. Okay, and so there it is, a gas mixture question. Very often, these gas mixture questions are applications of the ideal gas law, as it happens throughout this chapter. No surprise, it's the gas chapter. Just keep in mind when you're doing gas mixtures, very often you need to remember total pressure is the sum of all the partial pressures. Partial pressures can be calculated from the ideal gas law. If you have the information given, or if total pressure of the mixture is given, very often the mole fraction version is a little bit easier to work with. So practice a few of those. Keep this stuff in mind. Go forth and solve some problems. See you later.